Good morning, everybody. Sorry for this late start. So we continue. Just a second. We continue from the point that we have ended last week, and I will just remind you what this point was. Basically, we have proven that, or we defined S as a function of, I'm sorry, E, X, basically, and we called it entropy, basically stating that entropy is a function of state, and it defines the equilibrium of a system. Later on, we also found that we can write energy as a function of state. Sorry. I can also define the equilibrium state or any kind of a state. What we also found that entropy for equilibrium, or changes of the entropy from equilibrium state, will be always smaller than 0, basically meaning that entropy is at maximum with regard to internal changes of constraints, or changes of internal constraints. And for the energy, what we have found is that changes of energy under the operation of changing the internal constraint, energy changes will also be positive, meaning that energy is at minima in equilibrium. Minima with respect to what? With respect to local changes in internal constraints. And entropy is at maxima at equilibrium. Maxima with respect to what? With respect to local changes of the internal constraints. Now we're going to apply those variational ideas, okay, about entropy and about energy by performing a pretty standard task. We would ask if we have two systems, and we are going to change those systems a little bit, mingle with them a little bit. Can those variational principles somehow tell us what is the equilibrium and how the system is actually approaches to equilibrium? Okay. So, examples of variational principles. The first example is that we have two systems. Okay, the first system, there is some energy, a temperature, which we already defined last week, and of course the entropy. And there is another system, okay, with some energy, maybe different, temperature, I'm sorry, it's T2, which also can be somewhat different from the temperature of the first system, and the entropy. Great. Now I claim that those systems are in equilibrium. They are somehow connected, and they are in equilibrium. There is no escape of heat out of the system. Okay? So I define some sort of a adiabatic walls around the total system. No heat is escaping. My question is how T1 and T2 are related to each other. So it's the opposite question of usually how people define the second law of thermodynamics. The second law of thermodynamics basically states something about, in the usual sense, states something about the temperature of systems in equilibrium. Or if you bring two systems into a contact and then everything equilibrates, what is the relation between the temperatures? here we define, if you remember, the thermodynamic second law as property of a function that we named entropy. And we said that entropy is monotonically increasing with energy. Okay? And for any adiabatic process that starting from state A and reaching at state B, we know that the entropy must grow. Great. Now we want to go backward in the reverse direction and says, if we know that this thermodynamic law actually appears in nature, what should be the relations between the temperature? Usually people start with temperatures and then they go to the definitions of the entropy. We started with definition of the entropy and we want to see what happens to the temperatures. Okay, so how we deal with this? Remember, we want to use those variational principles. Okay? We want to say something about the changes of the entropy. Okay. Now, let's assume that, well, this is a system and we perform a variation of local constraints or internal constraints, I should say, internal, such that the total entropy is not changing, the total energy is not changing, the total temperature, well, there is not such a thing as a total entropy, so the total energy is not changing and the total entropy is not changing. So E is equals E1 plus E2. This is what we know. So the total energy is not changing. We also know that, well, we performed this specific changes in the internal constraint, then the entropy, while keeping energy constant, the entropy must what? The entropy, according to the variational principle, the entropy must decrease. So we apply this internal, mingle a little bit, change a little bit the internal constraints, and we know that delta S, when E is constant, and all the extensive variables are also constants, we know that delta S is smaller than 0. Okay? Because S is at maximum. Alright, what we know also, well, when we perform these changes in the internal constraints, the total energy was constant, so delta E equals delta E1 plus delta E2 stays constant. This is great, because out of this we immediately obtain that delta E1 equals minus delta E2. Fantastic. Now, using this simple relation, we go to the definition of the change, the global change of the entropy, and plug it in. Okay, so what is the global change of the entropy? It's delta S equals delta S1 plus delta S2. Why is that? Remember, entropy is an extensive quantity, so basically it's a sum of the entropy of system number 1 and system number 2. I'm sorry. Okay. So this is from one side, equals each change of the local end of the entropy we can change as the change of the derivative of the entropy with respect to the energy while keeping x constant, and the change of the energy, this is for system number 1, plus the change of the entropy for system number 2, which is delta S2 delta E x delta E2. All right. Now we can plug in the following relation. We know that delta S, delta E well, here we should play 1 and 1. Because E1 and E2, they're actually changing. It's just the global energy is not changing. So delta ds1 dE1, according to our definition of the temperature that we used last lecture, is 1 over T1. Okay. The same goes for the second system. ds dE2 equals 1 over T2. Again, we are using this relation between the deltas of the energy, and what we obtain? We obtain that delta S equals 1 over T1 minus 1 over T2, all of this multiplied by delta E1. Great. And as we know, this should be what? This should be smaller than 0. Okay, according to the variational principle that we used. Now, we haven't constrained the changes of delta E1. So delta E1 can be anything. Okay.
Why is it a minus there?
Where?
Plus
Here?
Yeah.
No, because delta E1 and delta E2 there have opposite signs.
Ah, you put delta E1.
Yeah. So what I did, I inserted instead of delta S1, delta E1, 1 over T1, delta E1, this is 1 over T2, delta E2, and then instead of delta E2, I introduced delta E1.
Okay.
Right? Now, think about it for a second. We have a relation that it's always either 0 or negative, while delta E1 is thus the changes of the local energy, of the energy of system E1. The changes of E1 can be positive or negative. This is a constant, this is a constant. We haven't variated them, right? What this means, so as long as this guy is unconstrained, either positive, either negative, this is have a specific sign, so let's assume that it is positive. Okay, if it's positive, and delta E1 is also positive, this relation could not hold. And we can also go the other way around. So the only circumstances under which this relation holds is when 1 over T1 minus 1 over T2 equals 0. Or, in other words, T1 equals T2. Which is obvious, right? We know that. We already learned that. Somewhere, somehow, from someone. If you have equilibrium and we bring two systems into equilibrium, the temperature of system 1 and the temperature of system 2 should be exactly the same temperature. The temperature is equal for all different parts of the global system. And this is what we have proved. Okay? Any questions about that? No. Okay. Now let's go to the case where, well, we have two systems. They are in different temperatures, so it's an additional example. We have two systems. They are not in equilibrium, and they brought into a contact. Again, then I impose adiabatic walls around it, and I want to ask myself what happens during the equilibrization process. Okay, so I had system 1. It has E1, T1, S1, and I have system 2, E2, T2, S2. Okay. They're not in equilibrium. T1 is not equal to T2, right? And the two systems are brought together. Now they have thermal contact. Okay. Heat is flowing. Something happens between the two systems. Nothing actually exits outside. Okay. There is no work done, maybe local work. And my question is, what happens to the whole system. What happens to the heat? Will the heat flow from T1, this system, to this system? How the energy will be transformed? So they are just in thermal contact. They are not performing any work upon each other. Okay? So there is the only change that happens that the system, I brought them into contact. Heat is flowing from one system to another, hopefully. Eventually, we know that the temperatures of both systems should be equal. Okay? How this actually occurs? This is my question. How this process occurs? So what we know now. So situation number one, the systems are in, each of them is in equilibrium. They're brought into system, and the starting point is this situation when these two systems are exactly at the same. They brought into thermal contact, and they start to equilibrate. Right? Now what I know is, well, I can define a state, a specific state of the two systems just before they were brought into a contact. Okay? This is state number one. Afterwards, I know that there would be an additional equilibrium state that would appear after a while. After I actually made them, I actually introduced this thermal contact. I waited a little bit. After a while, they will equilibrate. Okay, right. Now the change of the entropy here is positive, right? Because what is the definition of the second law of thermodynamics, as we stated it? If we start from a state A, and the system can reach state B in a adiabatic fashion, the changes of the entropies are always positive. So beforehand, I was doing something to internal constants. What I'm doing now, I'm just bringing them together into an equilibrium, okay? And I say, well, the entropy must grow. Delta S is greater than 0. They're greater for what? Before equilibration and after the system actually equilibrated. We even can state here that it's greater than 0. Any questions about the definition of the problem? No? Okay, so let's go on. So what we know here is that delta S1 plus delta S2, which equals to delta S, the total change of the entropy for the whole system, is greater than 0. Okay. What is delta S1? Again, we can go backwards to this definition. Delta S1 is the change of the entropy with respect to the changes of the energy for system 1 and for system 2. Okay? Which is basically delta S1, dS1, dE1, delta E1 plus delta, ds2, dE2, delta E2, this guy is greater than 0. Now, the only thing that I allow to exchange is the energy in the form of heat. The systems are not performing any work on top of each other. Okay, so there is something that happens between the systems. The heat is flowing from one system to another, maybe forwards and backwards. I don't really know. The only thing that I know is that the change of the energy appears without any work performed by the systems on each other. Now again, delta S1, delta E1 is what? Is 1 over the temperature. So this is 1 over temperature, delta E1, plus 1 over the temperature 2, delta E2. We know this is greater than 0. The total energy of the system is exactly the same, it's stayed constant. So delta E1 plus delta E2 equals delta E, the difference of the whole system, is exactly 0. All right. I'm sorry. So we introduce this into this equation. We obtain 1 over T1 minus 1 over T2 multiplied by delta E1 is greater than 0. Okay? So during this equilibration, what happened? Those are the initial temperatures. Eventually they will be exactly the same. This is the change of the energy in system 1. Okay? So what we can learn, and this happens always. Why it's different from this guy that we had previously. Here we did something with the internal constraints. All right? The system was in equilibrium, and we did something. We did something with internal constraints. This situation is quite different. We just introduced thermal contact, and we see how the system equilibrates. T1 and T2 were not changing during this process. In this case, T1 is just the initial temperature, the T2 is just the initial temperature. Eventually they will be the same. We know because eventually the system will reach equilibrium. All right, so this system, as opposed to, or this relation as opposed to this one, we know something about delta E1, right? Because what happens if T1 was greater than T2 initially? Okay? It could be. And consequently is that delta E1 is smaller than 0. And if T1 were smaller than T2, initially delta E1 is greater than 0. So what is this statement here? If we have two systems, we bring them in a thermal contact. Eventually, a heat will flow from a system with a higher energy to the system with a lower, higher temperature to the system with a lower temperature, and the change of the energy in system 1 will be negative. And the other way around. Okay? If initially the temperature of system 1 was lower, it will gain energy by this thermal process. Okay? Usually this is part of the definition of the second law, right? The heat is flowing from hotter systems to colder systems. Now what we have shown is that we can start with the definition of an entropy as some mathematical function and obtain this law. Great. Now, so we already defined some specific quantities. We defined the state of the system, we defined entropy, we defined energy. Okay? We can also define heat capacity. What is a heat capacity? A heat capacity is just how the total heat of the system is changing with temperature. Okay? C is delta Q, the amount of changed heat, by delta T. Okay. We can restate it and say, well, T dQ divided by T divided by delta T. And this guy, for specific reversible processes, is just what? ds dt. Okay? Remember this. How I got it? Remember that dE was delta Q plus delta W, the change of the energy, the change in the heat, the change in the mechanical work. It's not exactly mechanical, but it's work. And for reversible processes, we have T ds plus delta W. There is already a specific value. So for reversible processes, those guys are simply exactly the same. And this is why we introduced the change of the entropy with respect to the temperature. Sorry. Now, you already probably seen that there are two kinds of heat capacity. Because this is the total change of the entropy with respect to the temperature. But we usually, how we take derivatives, we constrain some of the variables to be constant during the process. Okay? Because we want to perform an adiabatic, not adiabatic, a reversible process during which we change some of the variables while keeping the others exactly the same. Okay? So we can define C and F, which is basically the heat capacity when the effective forces, generalized forces, are kept constant, okay? And which is basically T ds dt. And the external forces are kept constant. For example, Cp is T dot S dot T P. We keep the pressure constant and we measure the changes in the entropy with respect to the temperature, okay, while P is constant. Or we can generally define Cx. Okay? This is the heat capacity that can be calculated while keeping the extensive variables constant. Okay? Which is T ds dt x. And the usual and the simplest example is just Cv, okay, is T ds dt while V is constant. V here is an extensive variable. What actually is varied is pressure, while the I'm sorry, the volume is kept constant. Now, let me please remind you how our work is defined. Okay, so here I already used generalized forces, I used generalized extensive variables, and work was F dot dx. Okay? Work or a change of work. What it equals to? In most of the cases that we will use in this lecture and the following one, well, the one generalized force is pressure, and the extensive variable will be volume. So we have pressure multiplied by the change of the volume. We have seen that this is actually this behaves like an energy because it's simply force multiplied by distance. So the units are the units of energy. And we also will look on the different types of molecules that we have inside the system. I from 1 to R, mu I, P and I. So pressure, volume, and I. The number of moles of molecule I, okay? And mu I is what? Is the chemical potential. Chemical potential of molecule type I. Now we already discussed this in the previous lecture, but I just want to remind you, this is the usual mechanical energy. This is clear. But in order to be consistent and not consistent, maybe a little bit global, we can also define as part of this energy also changes in the molecular state. Okay? And the changes in molecular states are due to changes in the amount of the molecules. And as here P is a generalized force, the pressure is a generalized force, here the chemical potential is also some kind of a generalized force that defines the flow of the mass. Okay? Here is the flow of the volume, here is the flow of the mass. The flow of the different types of molecules from one part of the system to the other part of the system. And this is the generalized force. Okay. If we define the work in this fashion, the total energy now can be defined, we are going to use this lecture in the following one, as dE is just TdS. This is the thing that we already noticed. It's basically the heat component plus F dot dx. Okay? And this is work. Heat plus work. And the process is reversible. So dE is T ds minus P dV plus sum from y equals 1 till r mu I dni. Okay. And from here, what we obtain, that E is a function that defined by the state, and it's the function of what kind of variables? We see that the differential of E is the differential with respect to a specific variable. So what are the variables that define E? It's S, it's V, and it's Ni. So in order to define a specific state and define the energy of the state, what we need to define for this state is the entropy, the volume, and all the molecular components of the system. Okay. So energy is a state function dependent only on S, V, and 1 to NR. So remember, we define a state function entropy, and it was the function of energy, volume, and the molecular components, or we can define the state function as energy, and it will be a function of entropy, volume, and the molecular components. This is great. And we also can define the heat capacities, which basically define how the entropy of the system changes in the entropy, in the temperature, so defines the flow heats. And we basically can know everything about the system. But there is a problem. There is a problem in describing the system in terms of energy. Well, you can say, what's the problem? You need to know the entropy, you need to know the volume, and you need to know the molecular components. It's easy, right? In theory. When I come to an experimentalist and I say, well, you have a state and it is defined by S equals to 5, V equals to 3, and for example, N1 equals 7. He will immediately ask me, well, what is S? How can I measure S in my thermal system? And think about the physics of the 19th century. How can I measure S? I can control S, I would say, well, if you now change the S, the next equilibrium state will be such and such. You say, well, how can I change the S? I can change the volume. Maybe I can change the molecular components. I can maybe change the pressure, but how I'm changing the entropy? I can change the temperature, but the entropy, how I'm changing the entropy? And exactly for this reason, this is why it's actually a complicated value from the experimental perspective. Now, can we actually construct different functions of a state such that they will be dependent on different variables? Okay? So the quest now is, well, we have an energy. An energy defines the equilibrium state. It depends on specific type of the variables. I want to define the same equilibrium state using some other quantity, other state function that will be dependent on different variables. Okay? So is it possible, for example, to start from S, V, N1, and Nr and actually define the state by variables that are, for example, temperature, volume, and the molecular components? Is it possible? And the answer is yes. Exactly for this specific task, mathematicians already introduced something that is called Legendre transform. And Legendre transform is what is the mathematical tool that enables us to start from a specific types of variables, perform a Legendre transformation, obtain different types of variables, but only in the case that this variable and that variable are somehow connected to each other. They are conjugated variables. Maybe you remember when you studied analytical mechanics, this Hamiltonian stuff and how you transform variables, etc., that there is, the Legendre transform was already introduced there. The Legendre transform there was used in order to find the optimal type of variables in order to describe the system in a very simple fashion. Here the task is even easier. It's not that I need to find some sort of a naive variables or easy variables. For me, I want to find variables that are easy for experimentalists to handle. All right? So before we actually achieve this task of going from S to T or from V to P, etc., I would show you what is a Legendre transform. And it's a general mathematical tool. So we start from a function f, and f is a function of several variables, x1 till xn. Okay? It's not exactly those x's here, just dummy variables. All right? So I know what is the differential of f, d of f. Okay? It's the derivative of f with respect to x1 multiplied dx1 plus the derivative of f with respect to x2 multiplied dx2, etc., till the derivative, the partial derivative of f with respect to xn multiplied by dxn. Now we can call those df dx1, df dx2 as conjugated variables, meaning I define df dxi as some sort of a ui for any I, and rewrite the differential form using xi's and ui's. Okay. So df is u1 dx1 plus u2 dx2 plus etc. Plus un dxn. Okay? Haven't really done anything. F is still a function of all the variables that are appearing in a form of differentials on the right hand side of this equation. So x1, x2, etc., etc. Now let's define function g. G, and how I define it? I define it as f minus a sum from I equals r plus 1 till n of ui xi. Okay. What is this function? A general function. Now, why exactly I am taking I going from r plus 1 till n? Well, what I mean is, well, the order is not important. What I want to do is to start from a specific. So my general variables are x1 till xr, xr plus 1 till xn. Okay, so those are my variables of f. What I'm going to do is to actually take those variables and change them. I can do this in any other way. I can take only x1 and change this. Specifically, this ordering is very arbitrary. Just for the sake of simplicity of writing this on the board.
So it's like g is a function of r also.
G is a function of where, yes. But you will see specifically, still here I don't really know what are the variables of G. Okay, I'm just saying I know what the variables of F, here I have ui's and here I have xi's, and for me they are general variables, right? How I know what are the variables that define G? I take the differential of G and I'm looking at, okay, on the left hand side I will have a differential of G, on the right hand side I will have something multiplied by the differentials of the variables that define G. Okay? This is the way to actually know what are the variables responsible for changes in G. So what do? We take the differential. D of G equals of df minus sum from I equals r plus 1 till n d ui xi. Okay. What is df? df I already know. df is sum over j uj dxj. J goes from 1 till n. Here I have minus I goes from r plus 1 till n dui multiplied by xi plus ui multiplied by dxi. Okay, this is the differential of a multiplication. Differential of first variable multiplied by the second plus the first variable multiplied by the differential of the second variable. Okay, let's rewrite the sum as a sum from j equals 1 till r uj dxj plus a sum from j equals r plus 1 till n uj dxj minus a sum from I equals r plus 1 till n xi dui, right? Minus a sum from I equals r plus 1 till n, and here I will have ui dxi. And the only difference between in this term and this term is that I use different dummy variables, I on j. So basically, this guy and this guy are gone, and what I left with is that dg equals a sum from, let's change the variables, I equals from 1 to r ui dxi, minus a sum from I equals r plus 1 till n xi dui. Now we see that our new variable, our variables for g are xi and ui. So I have now r variables that are x's and n minus r variables that are u's. Right? So by performing this very simple transformation, I define a different state function that now depends partially on the original variables and partially on the new variables that are conjugated to the old ones. What I mean by conjugated, those u's will have the partial derivatives of the original f. Okay? So in our perspective, p and v, okay, s and t, those are variables that are somehow related to each other, they are conjugated. Okay? So what this Legendre transform means for us, that if we take energy, that is, for example, defined in, let me write it down, energy is written in a very specific form, right? How do we write energy? Or differential for the energy. The differential for the energy was dE equals T ds minus P dV plus sum from I equals 1 till R mu I dNi. Okay? And we defined E as a function of S, P, N1 till NR. Now, what Legendre transforms teaches us? It teaches us is we have this kind of a function, E, and those are our variables. We can change easily the variables by the respective conjugated variables, meaning the partial derivatives that are stand in front of the differentials of the original variables. So, S and T can be swapped. P and V can be swapped. Mu I and Ni can be swapped. Right? So, for example, let's define a function A, which we want it to be a function of pressure, the molecular composition, and not of the entropy, but of temperature, because for the experimentalist it's much more easier to control the temperature. He knows how the temperature, he knows how to relate it, he knows how to measure it, and he knows how to relate it to the amount of heat or the heating, etc., etc. So we want to define a state function that will depend on T, P, and N1 till Nr.
Didn't we write volume instead of pressure?
Yeah, you're right. Of course. This is V. Yeah. S, V, and Ni. Yeah. You're right. So what we do, according to the Legendre transform, we take the function new function A, we take our original function E, and we subtract from it what? The variable that we want to change, S, and the new variable that we want to introduce, which is conjugated to S, which is T. We can write the differential of dA. What we will get, that is written as minus S dt minus P dV plus a sum of I equals from 1 till R mu I dNi, which basically states that A is a function of T, right? What we have here, T, V, and all the Ni's, N1 till Nr. What is this A? It has a name. It's a Helmholtz free energy. Why it's important? Because A, it defines the equilibrium state. B is a function of some other variables that are maybe easier controllable. Temperature, volume, and the composition numbers. I'm sorry. So A, Helmholtz free energy. All right. Can we define some other variables? Well, basically yes, because we can start with the energy, which is a function of S, V, and let's look like only on one single specific n because, well, we can have a lot of n's. So what kind of transitions are permitted? We already shown that we can transfer our variables to T, V, and N. What else can we do? So here we swapped S and T. Okay, we can swap V and P, right? So we can have S, P, and N. What else can we have? T and P, right? So we can swap a lot of variables together. We don't need to actually each time to swap only one of them. So we can have T and P and N. Okay? Can we have something which is P and V and N? Okay. So this is allowed. Is this transformation allowed? No, because they are not conjugated variables. What we happen here is we swapped S with P. And if we will go to the definition of the energy, S is not a conjugated variable of P. P, I'm sorry, is a conjugated variable of V. Okay? So those are the only transformations that are allowed. So historically, what functions are there, which basically what kind of Legendre transformation I can perform for my energy. Okay. So there is G, which is E minus Ts minus PV, okay, which is G is a function of T, P, and N. It is called Gibbs free energy. Gibbs free energy. And we can write a differential of G. D of G equals to minus S dt plus V dP plus a sum of I, or I'm sorry, plus mu dN. Okay, so this is Gibbs free energy. We can also have H, which will be equals E minus PV. Okay? And it's as a function, it's simply E plus PV, and it's as a function of H is a function of S, P, and N. S, P, and N. It's called enthalpy. And dH is simply TdS plus VdP plus mu dN. Why are those functions important? Depends on what exactly the experimental procedure you want to perform. It depends how you want to define your state, and more specifically your equilibrium state. What are your variables? Are your variables entropy and pressure, temperature and volume, temperature and pressure? Depends on your experimental apparatus. You have apparatus that controls temperature and pressure. Great. You should use Gibbs free energy. You have an apparatus that controls temperature and volume. Well, you should use Helmholtz free energy. Great. The transformations from one to the other is very, very, very simple. Now, what about the variational properties? You remember this was an important aspect. We know that S is maximal at the equilibrium with respect to what? To changes in the internal constraints. E was a minimal. Okay? So if you look, what is delta E? Delta E was greater than 0. Delta S was smaller than 0. What are the variational properties of the new functions, new state functions? Okay. So for example, we take delta A. What we will have over there? Okay. We keep temperature constant, we keep volume constant, and we ask ourselves, under the change of internal constraints, will be delta A greater than 0 or smaller than 0? Again, remember this procedure. We start from equilibrium. We are doing something to the system by introducing a local constraint, and we see, well, in this case, the Helmholtz free energy is going up or going down. Now, this is easy to see because we know that E here comes with a positive sign. S here comes with a negative sign. Okay? T is kept constant. So if we introduce a local internal constraint, E will get bigger, S will get smaller, but because of the minus S, it will be bigger again. So delta A is greater than 0. Is greater than 0. Okay? The same holds for delta H. Is greater than 0. And the same goes to delta G. So for enthalpy, for Gibbs free energy, and for Helmholtz free energy, the variational principle means that if we do something with internal constraints, the equilibrium is always a minimum. Okay? Delta G is greater than 0. Here we remember what are kept constants. Delta A, T, and V were kept constant. Delta H, S, P, and N kept constant. And delta G, T, P, and N kept constant. All right. Now that we introduced new functions and we introduced new variational principles, we can ask ourselves, okay, so how maybe we can relate different quantities or changes in different quantities. So I want to see how the entropy is changing with volume, right? Can I go and measure this? Experimentalists cannot measure entropy. Entropy is not really well defined. We don't really have a form for entropy. Okay? Now, maybe I can measure how temperature is changing with volume, and by knowing this relation, I can go backwards and describe how the entropy is changing. Why? Because, well, I can maybe I can use entropy, and afterwards I can transform this information to the changes of the energy, and I know how the entropy will change there, etc., etc. So the goal here now is to relate the behavior of different quantities, or the derivatives of various quantities, by describing them as derivatives of other quantities. And this is what is called Maxwell relations. A Maxwell relation is basically the statement: if I have a function of state, I assume that it's differentiable to the infinite order, and then if it's differentiable to at least to the second order, there are some relations between the second order partial derivatives, right? And by using those relations of second order derivatives, I can maybe transform from behavior of one variable to the behavior of the other variables. So for any function of x and y, okay, we can write that df is just a dx plus b dy. Okay? Now, if f is at least differentiable to the second order, what we know and what we learned a while ago in calculus class is that df dx dy equals square f dy dx. The order of the differentiation, it doesn't matter. Okay? So what happens? So if f equals, or differential of f equals a dx plus b dy, what we know is that d a dy equals that db dx. While what? Here I keep constant x, here I can constant the y term. Alright? Can we see an example of this? Why it's important? Because it's basically a statement of a very trivial fact that we already know from calculus. Let's look on the Helmholtz free energy, right? So the Helmholtz free energy, dA, equals to what? Minus S dt minus P dV plus mu dN. So what actually Maxwell relation says? That the derivative of this guy with respect to V equals to the derivative of this guy with respect to T. Okay. So ds dV, while keeping T constant and N, equals to the derivative of d of P with respect to T while keeping volume and N constant. Okay. So we want to see how entropy is changing. We don't really know what is entropy or how to measure it, but we can measure pressure and temperature. Go ahead. Measure the changes of the pressure with respect to the temperature while keeping the volume constant. Gives us exactly how entropy is changing with volume when keeping the temperature constant. Okay. And by this way, we can continue and define a very large set of relations between derivatives of different quantities. It's actually somewhat trivial and not very interesting, but found to be useful. Additional example, it's the Gibbs free energy. Okay? What is the Gibbs free energy? dg equals minus s dt plus v dp plus mu dn. So derivative of this guy equals to the derivative of this guy. With respect to, this is derivative with respect to p, derivative of this guy with respect to t. What we obtain is ds dp t and n equals minus dv dt with p and n. An interesting example. How this, for example, can be measured in practice. We can go, additional example. CV, okay, the heat capacity when volume is kept constant is temperature multiplied by the derivative of the entropy with respect to temperature. V and n is constant. Okay, again, I don't really know what happens to the entropy, but I can now relate different derivatives of the heat capacity and see how this works out for me. Okay? So let's take the derivative of CV with respect to the volume while keeping the temperature constant. Simply temperature multiplied by the derivative with respect to the volume of what? Of this guy. ds dt v and n. Here, what is constant is t and n. I can swap the order of the differentiation, right? Or even easier. I can say what is, I swap the order. So here I take a derivative with t, and afterward the derivative with respect to v. I can say is just t multiplied d dt d dv of s. Here I will have t and n. Here I will have v and n. Right? And ds dv, while keeping temperature constant, this is this relation. Okay? This is derivative of the pressure with respect to the temperature. So it equals to t d dt of what? Of dp dt. While keeping what constant? Volume and the compositional number. Volume and compositional number, v and n. And eventually what I obtain is that C dCV dV under constant temperature, it equals to the temperature multiplied by the second derivative of the pressure with respect to the temperature, keeping volume and n constant. This is a measurable quantity. Okay? I can take a pressure, I can imagine myself some specific volume, and I have an arm that controls the pressure, and I can heat up the system a little bit and increase the temperature, keeping everything in an equilibrium, and I can see how the pressure is changing. I can go and actually measure this. Very, very simple, even for the physics of 19th century. By measuring this, I exactly know, well, how the heat capacity is changing with volume. Okay. So after the break, I will describe what happens, for example, for the heat capacity when the pressure is kept constant. We continue with our examples for relation between different quantities, or more exactly for the relation between the derivatives of different quantities. So we stopped when we obtained this specific relation, the derivative of the specific heat, CV, with respect to the volume, is obtained as the second order derivative of the pressure with respect to the temperature. Now I want to show you how the specific heat, Cp, basically a specific heat taken when the pressure is kept constant, is changing, is related to the specific heat when the volume is kept constant. So what we have here, additional example. The relation between Cp and Cv. Okay, so remember, the specific heat Cp is just temperature multiplied by the derivative of the entropy with respect to the temperature, while keeping pressure constant and the molecular number also constant. And what we are going to perform right now is, again, playing with the variables, making basically substitutions of one variable with respect to the other, and eventually obtain some relation, some formula that will include Cp, Cv, and something else. What is usually something else? Something that is easy to control by in an experimental situation. For example, pressure, volume, temperature. Okay. So let's start with defining what is the differential. What is the differential of the entropy? Okay. So differential of the entropy, ds. For simplicity, we will keep the molecular number n constant. It's just simply the derivative of S with respect to the temperature, keeping volume constant, multiplied by the change of in the temperature, plus the derivative of the entropy with respect to the volume, keeping temperature constant, multiplied by dV. Okay. What is dV? We can say that dV, again while keeping the number of the molecules constant, is simply the change of the volume when we change the temperature multiplied by T. Okay. Plus the change of the volume with respect to the pressure multiplied by dP. Okay. So here the pressure is constant, here the temperature is constant. Volume we can control in several ways, changing the pressure or changing the temperature. All right, so now let's substitute this guy into here. What we obtain, so we have ds n equals to ds dt constant v dt plus ds dv constant t multiplied by dv dt constant p multiplied by dt plus dv dP, constant t, multiplied by dt, is now a square bracket. Okay, let's regroup what we have. What can we regroup over here? This term and this term. Okay, because now the variables are t and p. So we have ds n equals ds dt v plus ds dv t multiplied by dv dt p and n. Okay. All of this multiplied by dt. Okay. And the additional term that we have ds dv dv dp plus ds dv t multiplied by dv dp dv dp t dp. Okay, so let's see. So we have ds equals something multiplied by dt plus something multiplied by dp. Now what I'm claiming is, in general, what we should have, ds for n is ds to dt multiplied, all I'm saying is that ds to dt, so we have here ds n equals ds to dt, what we kept constant, p and n, right? Multiplied by dt, we have changed the variables, plus ds to dp, t and s kept constant, multiplied by dp. So this guy and this guy are exactly the same, right? We have a uniqueness of representation. So now what we have found, what is the derivative of entropy with respect to the temperature while keeping pressure constant, how we can describe it by other terms, right? And why we have needed this? Because the derivative of the entropy with respect to temperature when pressure is constant is exactly Cp. Okay? So we have now the ds dt, p and n constant equals ds dt, v and n constant plus ds dv, t dv dt, p and n. Okay. Now, what is this guy? Is just Cp multiplied by 1 over t. Okay. What is this guy? Is just Cv multiplied by 1 over t. And here we have ds dv multiplied by dv dp. But we know what is ds dv, right? It is dp dt, we already have shown this, plus dp dt for constant v and dv dt constant p. Okay. Okay. So this is already some sort of a relation between Cp and Cv. Okay, we have Cp on the left-hand side and we have Cv on the right-hand side, and we have here P with T volume constant, V with T pressure constant, and what I want to show you is that we can make this quantity over here somewhat different. Okay? A little bit different. So I want to perform an additional transformation in order to change this quantity into something else. Basically, eventually I want to describe Cp and Cv in terms of quantities that are called isotemporal compressibility, isothermal, and thermal expansion. I will show you what those quantities are in a second. But first of all, let's see. One can say, well, this is somehow looks familiar because it's P with respect to T, V with respect to T. Maybe they are somehow related, those quantities. Okay? Now, I want to make a specific transformation which is quite general for 3 variables. If I have 3 related variables, I want to show you a specific relation which starts like this. So my variables are x, y, and z. X, y, and z. And I know that dx equals dx dy plus dx dz. Okay, this is keeping z constant. This is keeping y constant. Also, I know that dz, so x is a function of y and z. Or I can say, well, z is a function of x and y. dz dx, keeping y constant, plus dz dy, keeping x constant, dy. Now what I can do, I can introduce the differential of dz into this first equation. What will I have? We'll have dx equals dx dy z dy plus dx dz y multiplied by what? By the right hand side of this equation. It should be dz dx y dx plus dz dy constant x dy, right? And now we will play a little bit more. Why? Because here you see we have some specific functions. So we have dx dz multiplied by dz dx while keeping y constant. So x is a function of z, z is a function of x. All of this is just will be equal to 1. Okay, so we have dx dz y constant, dz dx y constant. Okay, so the same variable is kept constant for those 2 derivatives. Okay, so this should be equals to 1. Okay, and then we have dx equals dx dy with respect to z dy plus this guy multiplied by this guy is just simply dx plus this guy multiplied by this guy, which is plus dx dz y dz dy x multiplied by dy. This dx kills this dx, and eventually we will obtain that dx dy z plus dx dz y dz dy x, all of this multiplied by dy equals to 0. Okay? Which means that for general three variables that are a function of one another, we always should have that dx dy z equals minus dx dz y multiplied by dz dy x. Okay. And this is already a general relation. Now look on the right hand side of this equation. If we call P x, T z, and V y, what we have here? dp dt, V dv dt, P. So this means, well, I should put it, this equation basically says that dp dt, while keeping v constant, is equals minus dp dv, keeping t constant, dv dt, keeping p constant. Okay? I can introduce this to the star equation. What is a star equation? This guy over here. And what I obtain? I obtain that Cp minus Cv equals to minus T dp dt, I'm sorry, dv, dp dv, right? dp dv t multiplied by dv dt p squared. And there are all kind of different games that one can perform changing the different variables. So each time what you do, you just use very simple laws of calculus for changing variables, as this one that I described over here. Now it looks like a little off from what we really usually know, because we can say, well, dx dz dz dy should be just dx dy, right? They should cancel each other. But one must look that y and x are different here. Okay, so here y is kept constant, here x is kept constant. This is why we have a minus sign. Now, this guy called isothermal compressibility. And this guy is just thermal expansion. Expansion. There are important experimental values that are easily measured, and from them one can easily construct the differences between the heat capacities with respect to the pressure and with respect to the volume. Okay. So where we stand currently, remember we have defined two thermodynamical laws, the first and the second. We defined functional states. We defined equilibrium states. We defined what happens when we approach to equilibrium. We defined variational principles. And we can go from one function of states to another, to additional auxiliary functions. And we can relate the derivatives of a lot of quantities one to another. We can change variables very, very easily. Okay? But can we now go and construct the functions themselves? Not just the derivatives, but the functions themselves. Okay? Can we construct the energy? Not the derivative of the energy or differential of the energy. Can we construct the entropy? Etc., etc. Now here, or so far, I'm sorry, we only learn how to construct or how to relate different derivatives. usually how one can construct a function. If you know the derivatives, you want to actually obtain the function itself. You perform an integration. The problem that we have only partial derivatives, so this is a little bit tough. Okay? But here, our initial assumption, which holds true, comes as a great help. What we have assumed about energy, for example, it's an extensive function. Okay? This is a great simplification when one actually wants to construct the function itself, and only thing that he knows, he or she, the partial derivatives. What we can see that extensivity leads to homogeneous functions of the first order and this, by Euler Theorem, leads to construction of the function based only on the partial derivatives. Okay? So for extensive quantities, the knowledge of the partial derivatives is sufficient in order to construct the function itself. How and why, we'll see in a second. So first of all, what is a homogeneous function, how I can define it, and why extensivity basically means homogeneity. And what is this Euler theorem for homogeneous functions of the first order? We'll come to this in a second. Okay, so our definition is, so let's start from energy. Energy is a function of what? Of S and extensive variables S. We know that the differential of the energy is TdS plus f dot dx. All right. What happens if we make the following transformation? X goes to lambda x. We linearly increase our extensive variables. Okay. What should happen to the energy? It also should increase, right? Why? Because it's extensive quantity. I increase the size of my system because of the extensivity of the energy. The energy also should increase in a linear fashion. How one sees that? Okay, so we know that when x is multiplied by some lambda, lambda is a scalar, entropy is extensive quantity, it also grows linearly. Okay. So we take this and plug it into the differential itself. So entropy is extensive. It grows linearly with the size of the system. And since we increase the size of the system in a linear fashion, S is increased in a linear fashion. Okay. And now we can ask ourselves, what is energy of the new system that was increased by the factor lambda? So lambda s, and here I have lambda x, right? So we know that dE equals T multiplied by d lambda s plus f d lambda x. Those are my new variables. They have grown bigger. I'm sorry. basically this means we can take lambda out of this differential. So we have here lambda t ds plus lambda f dot dx equals lambda multiplied by t ds plus f dot dx. And what I obtain from here, this is d of e of lambda s lambda x. So dE lambda s lambda x is equals to lambda multiplied by dE of s and x. This immediately means that E of lambda s lambda x is equals to lambda of E of s and x. This is our extensivity property, a linear growth. We increase linearly the system, the energy grows linearly. But this is also a definition of the homogeneity property. Okay? Because a function is called homogeneous of an nth order if g of lambda x equals lambda to the power of n multiplied by g of x, g is a homogeneous function of s of x of nth order. So basically, in mathematical fashion, our energy is a homogeneous function of all its variables, and the order of homogeneity is 1. Okay? Great. The moment we have established this, we can use something which is called an Euler Theorem of homogeneous function for homogeneous functions for the first order. I can go now and state this theorem, and actually I will prove the theorem of Euler. And this theorem helps me to obtain for any homogeneous function the knowledge what is this function is by only knowing its partial derivatives. Okay? So Euler theorem for homogeneous functions of the first order. So if g of x1 to x to xn is a homogeneous function, which basically means that g of lambda x1, lambda x2, lambda xn equals to lambda for g x1 t of xn. Okay. Then g is simply gx1 to xn, and simply a sum of dou g dou xi xi. This is the statement. If I have a function of many variables, the only thing that I need to know is the partial derivatives. I take each part of our partial derivative, multiply it by the variable, sum over all my possible derivatives, and I have the function. So the moment I know what are the variables and what are the partial derivatives, I know the function itself. Great. Now, how it helps us, I'll prove it in a second, but how it helps us, think about it for a second. We know how to relate, for example, derivatives of S and derivatives of E. And S is extensive property, E is extensive property. We know how to define their derivatives with respect to measurable quantities that are related to pressure, temperature, volume. Okay? So by using this theorem, we can go backwards, work backwards, and actually say, well, I know the derivatives, I know what they are the variables, I know what the function is. Okay. So now let's prove this theorem. It's actually quite nice. Any questions? Okay, so we start from defining, let's define for any I, ui, which is simply lambda xi. Okay. I take my different original variables and I just not transforming and naming in a little bit different way. Lambda xi is named ui. Now, I can now write g of u1, u2, and un, right? This is basically what it is. It is g of lambda x1, lambda x2, and lambda xn. Now, I take the derivative of g of u1 till un with respect to what? With respect to lambda. And what it is, I need to take a derivative of g of lambda x1 till lambda xn with respect to lambda. But g is homogeneous, which means that g of lambda x1, lambda x2, lambda x3, lambda xn is simply equals to lambda g of x1 till xn, d lambda. So lambda is only over here, it's a linear function, and obtain that this simply equals gx1 till xn. Okay? So dg d lambda, when g is defined as a function of u's, is simply equals to g of x1. This is a specific statement that we should remember. Now let's take the differential of g with respect to u's. dg u1 till un equals to the sum of the derivatives, partial derivatives of g with respect to ui's, dg dui, and here I have all the other uj's constant, all the other u's are constant, multiplied by what? dui. So I just have written what is the differential of the g function is. Now, what is dg d lambda? dg d lambda, okay, dg d lambda, we can write in the following fashion. We can write that dg equals dg d lambda d lambda, right? So we only swap those guys over here. So we take this guy all the right hand side of this equation, and we compare it to the right hand side of this equation when we have taken the derivative with respect to what? To lambda. We have changed the variables. Okay. I'm sorry. We can write that dg d lambda equals to the right hand side when we have taken the derivative with lambda, with respect to lambda. It's, there it is, a sum, by the way, here it's a sum from 1 till n. Here is a sum from 1 till n. Dou g, dou ui, dou ui, dou lambda. All right? Yes. Dou lambda. All the xj's kept constant. All the uj's are kept constant. Okay, so this is the connection between dg when I'm changing lambda, general, keeping all the x's constant, and the right-hand side of this equation over here. But what is this guy over here? Remember, what is ui? Ui is lambda xi. So what is the derivative of ui with respect to lambda? Just xi. So I can write this as a sum from I equals from 1 to n, dou g, dou ui, uj, xi. But we already know what dg d lambda means. We started this here. dg d lambda of u1 till un, we know it equals to g itself. All right? So generally, g of x1 to xn equals to the sum of I from 1 till n dg du I uj. Here I will have only xi. This is true for any alpha, for any lambda. I haven't assumed anything about those lambdas here. This is a very general statement. You take a general lambda, you make this transformation, and you can represent your function with respect to its derivatives to the new variables multiplied by the old variables. What happens when I take lambda equals to 1? A very specific case. Okay? So for lambda equals 1, ui are just xi. Yeah? So what we obtain here is that g x1 to xn equals to the sum from I from 1 till n dg dxi multiplied by xi. This is exactly what we wanted to show over here. Okay? This is the proof, QED. This is the proof of the Euler Theorem for homogeneous functions. Okay? Homogeneous of the first order. If you have a function which is extensive, it basically means it's homogeneous, then the only thing that you need to know is the partial derivatives, and you're done. You're always done. Yeah? No? Hope. Eventually someone would ask a question. Okay. How can we use it? Let's see how we can now define the energy by using this Euler theorem. Okay. It's very simple, extremely simple. Okay. Example. Energy. So we know that E is a function of S and X. Okay? We can write, and it's an extensive function, right? According to Euler Theorem, E is equals to dE ds multiplied by S plus dE dx multiplied by x. So here S is constant, here is X is constant. This is the outcome of the Euler Theorem. You have two variables. Okay? You need to take the appropriate derivatives, partial derivatives of the original function E with respect to those variables, multiply by the variables, and here you have E. Not dE, but the E itself. But what is dE ds? We already know this guy. This is how we define temperature. So this is temperature multiplied by S. What is dE dx? F dot x. Okay? An immediate outcome of the Euler Theorem. You don't need to compute anything. The moment you know the derivatives, you define them, you found them, you have related them to the other derivatives of other quantities, you plug it in, multiply it by the variable, voila, you have it. Now, starting from here, you already can compute other stuff that were obtained from experimental fashion. So, for example, Gibbs-Duhem Equation. What is this Gibbs-Duhem equation? It was found experimentally too. S dt minus V dP plus N d mu equals 0. This is the Gibbs-Duhem equation for some specific transitions. Okay? This always holds. How can we prove this? Okay? So we can start with the definition of the energy. As we already have it here. From the one side, and from the other, take the differential representation as we already know it. So E, according to this equation, is Ts minus Pv, right? Plus mu n. Okay, this is this equation, what it tells us. This is from one side. From the other side, we know that d equals to Tds minus Pdv plus mu dn. We go one little step forward and we say, okay, this you know, but let's take the differential of this equation. dE equals to dTs minus dPv plus d mu n. Basically says dt multiplied by s plus t ds minus v dp minus p dv plus mu dn plus n d mu. This is dE. So it should equals to this guy, right? That we already know. TdS minus pdv plus mu dn. We substitute this guy from this guy or this guy from this guy, it doesn't matter. And eventually we obtain that s dt minus v dp plus n d mu equals 0. You play with the definitions and eventually obtain the representation. All these quantities, Gibbs, Helmholtz, enthalpy, energy, very easy to treat, very easy to handle. You just have to take the different derivatives. You have to represent the transformation of the variables properly. You can obtain different interesting, well, not so interesting today already, quantities and relations between for the observables that you can measure. All right. Now, the moment we already have defined equilibrium states, we define how we can treat the functions of the states, and we even said something about variational principle of the states. We basically know almost anything about states in equilibrium. So what is then interesting about thermodynamics? Well, we heat it up a little bit, we change the pressure, we change the volume. Everything is changing in this we can describe the changes in a quasi-static fashion, and we can relate one equilibrium to another. This is somewhat very dull or not interesting. What is interesting about thermodynamical changes? Sometimes when we perform this change, we change one extensive variable, we change the pressure, or we change intensive variables, we change the temperature. The system abruptly changes from one behavior to another. Very simple example. We have water, we cool it down. It's water, it can flow, right? We cool it down, it becomes ice. Ice is a solid. You can break stuff with this. It does not flow at all. Okay? So something have really changed during this process. Again, the same stuff goes when we heat it up. Okay? We can go from water to vapor, okay? To gaseous states. So there are different states, different phases of matter, okay, that are achievable by by the changes of specific extensive or intensive variables that define the system. This is very interesting because we haven't encountered any of this in our description of equilibrium. Okay? How can we see that while changing specific quantities, specific properties, the system can somehow reach a different state? Reach not a different state, but a different phase. Okay? How this can be actually observed? Because something will have to change. For example, compressibility of ice or the heat capacities will be there just continuous functions. Here we use that everything is differentiable. Everything is continuous. What will start to happen that at specific points this assumption breaks down? Actually, what we will see then when specific assumptions about differentiability start to break down, we would see phase transitions from one phase to another. For example, as I already said, there is behavior of water, right? So if we take intrinsic volume, so the volume divided by n, and we'll look on the temperature, and we would want to see how the self-volume of the water at constant pressure changes as a function of the temperature. So we know for Celsius there is a temperature 0, and what we will have that the volume, intrinsic volume, goes up as we heat up, starts to go down. At some point we'll have a minima, and this is the critical point that something interesting happens because here it's already ice. Okay? So we want to approach those specific points. Okay? We want to approach those so we can continue, and nothing actually happens with the ice. But maybe some other quantity, like the heat capacity, or even something else, will actually behave in a very unpleasant fashion, non-differentiable maybe. Maybe we'll have divergences, but here we know that there is water, there is ice. And this strange behavior at this point, it becomes very interesting. Here we can observe and describe everything by what we already learned here. For the ice, again the same. Well, ice at this temperature or ice at that temperature. We don't really care much. Something happens here, and those specific points we want to actually study next. By the way, what we can learn from this behavior of the intrinsic volume of the water is function of the temperature, so P equals 1 atmosphere. What exactly can we learn from the behavior of this graph? Okay, so what can we learn? For example, when we learn that ice actually flows on top water. You know, when everything freezes up, it's only the top part of the water that freezes up, and not all water, right? Why is that? Why in the winter it's only the facial parts of the ocean or of the sea, if you're near an Arctic Ocean, that freezes up? Why it's not happens all the way down? And why actually ice is not below the water? So this is exactly this behavior of intrinsic volume with the temperature. Because think about what happens. Okay, think about what happens. Is we cool everything down, the intrinsic volume becomes lower, okay, becomes lower, everything becomes heavier. This is okay. Now, at specific point, I think around 4 or 3 Celsius, we have a minima. 4 Celsius, 0 Celsius. We have a minima, and then the intrinsic volume starts to climb up. What it means? It means that here the cooler water becomes lighter, and it actually stays above the colder water, the hotter water. Okay, so as we go to the sea, in this specific very small range of temperatures, the top side of the water will be colder than the water that is deeper inside. So only the top side of the water will eventually become ice. The water, so if you look, this is cold, and here we'll have hot. The cooling process happens over here. So the cold water it's lighter than the hot water. It stays above the hot water because it's lighter. Okay? And eventually this guy becomes ice. And only the part that's actually the facial part, it's what becomes ice. It freezes up. It's a little bit non-intuitive if you think about it from the perspective of your everyday experience. Okay? So in your everyday experience, what happens is that hot water goes up. Flow of hot water. Where you see every day, I mean at least most of us, see that the hot water actually goes up. Okay? Where we see this? In a regular kettle. Okay? So let's assume this is our kettle. Here we have spiral that heats up the water. Why the bottle eventually, all the water in the kettle has exactly the same temperature and it boils all together. Okay? It's not only that this part boils or this part boils, everything is boils. Basically means that the water is very well mixed up inside the kettle. Why it actually happens? Why we have a flow of hot water to the top and why everything is mixes? Well, we're heating over here, so we would say, well, all the hot water is here at the bottom of the kettle. Okay, why everything is mixes up? Because when we heat something, the volume, the intrinsic volume, goes up. And as it goes up, okay, in this direction, the hot water becomes lighter than the cold water. Okay? So if it's lighter, it goes up. Okay? There is this boil force. And the cold water goes down. So we have this circulation of hot water up, cold water down. This cold water becomes a little bit more hotter than this water over here. And so we have a circulation of water in the kettle. Every day we see this circulation. This is why the water boils, not immediately, but all the water is hot in the kettle. Here we have only one specific piece, the top piece of the water that freezes up. One can say, well, it's counterintuitive. But what actually happens is that we have a minima. And here, as we cool down, the water becomes lighter, and so it stays up. The circulation is not changing. Beforehand, when we cool down the top part, it just goes down, and hot water goes up. So everything comes to this temperature around 4 Celsius. Very cold water. Above that, or below that, actually it's only the cold water stays up and never goes down, and it eventually freezes. By the way, so I described you here how the kettle works here on the ground. Why we have the circulation? Because eventually we have a gravitational force, right? Heavier things go down, lighter things go up. What will happen in the space? Will the regular kettle work in space? How exactly they boil water in the space station? The regular kettle won't work. What actually happens is that they have to mix everything by some mechanical apparatus. Okay? So there is a mechanical mixer. It mixes all this water in order for the water to heat up. Otherwise, only this small part will be very hot. Okay, the kettle will go down, and eventually, the part of the water will be still cold. So, just an interesting notion. Okay, so we start to talk in the 10 minutes that we have left. We start to talk about different phases. So phase, as already explained over here, so for example, ice and water is a phase. So we have gas and water. It's also a different phase. When I look on the system, I can describe it as constructed many subsystems. Each of those systems have different phase. Each of those systems have different phase. Each of the systems have different energy. This would be system 1 with phase 1. This is energy 2 with phase 2, E3, E4, E5, etc., etc. So if I have 5 different phases, I will have 5 different energies, which are prescribed. Each of these energies is prescribed to a specific phase. I already told you that generally I assume that energy is an extensive property. So E is equals to E1 plus E2 plus E3 plus E4 plus E5. Okay. Or if I have new energies, I can say in general E equals to a sum. I goes from 1 to nu, E I, where nu is the total number of my phases. Now, you already asked me last week, well, there is a problem with this, because maybe there is interactions between this system and this system. And this interaction can actually change the energy, right? Because there is the energy that inside this, and there is the energy that comes due to the interactions between the systems. Okay? This is what is called a surface energy. Okay? So we can describe an energy in the bulk and the energy that it's associated with the interface between the two phases. Right? So there is, for example, take an ice and water. So you have a chunk of ice floating in a big pool. So there is an energy, internal energy of the ice. This is internal energy of the pool. And this is some energy that associated with how many ice molecules are in interactions with the molecules of the water. The same molecules, but the phases are different. So the molecules of the water are free to go wherever they like. The molecules of the ice are very constrained to a specific position with respect to other molecules. So maybe this energy over here is actually important. Maybe then, if we take this energy into account, this extensive property won't hold. Okay? Remember our discussion, I said, well, if everything is macroscopic, it won't matter, but when we go to the microscopic systems, for example, an atom, okay, then there is an energy of the nucleus, there's the energy of the electron, and if you separate them both, the total energy does not equal to what it was before, because there is this interface energy or the connection energy, whatever you call it. Now what I want to claim, it's a very general claim about, I will introduce something which is called scaling approach, is that for macroscopical systems, the energy is always an extensive property, extensive quantity, I'm sorry. So how it goes? 7 minutes, great.
But that means that I can forget the surface of the ice.
Yes. It's basically negligible when you're comparing it to the energy of the total system. If the only thing that you're interested are actually the energy of the surface, it's important. For example, we know that the energy of the surface of the water is very strong. You can actually take a needle and place it on top of a glass of water and it won't sink downwards. Why? Because it had to overcome this surface energy. Okay? And if you place it inside the water, it will just immediately go down. So there is something very special about this. But if we compare the two, I will show you that it's just non-existent. Okay? So the way I want to show you how this is done, I would use something that is called a scaling approach. So scaling approach is something that I can always invoke when I'm dealing with macroscopic systems with a lot of quantities. Scaling approach. So we know it's a hand-waving argument. This is what scaling approach is, hand-waving argument that's based that a specific quantity is very, very, very big or very, very, very small. Okay? So what we have in our scaling approach? We know the energy of the surface is proportional to what? To the total number of particles on the surface. This is our assumption. Now let's take a three-dimensional system. So the surface must be two-dimensional. What it means, E surface goes like N surface. Okay? N, not N surface, N, the total number of particles in the three-dimensional system. Now I know that E system is proportional to n. Okay? So what I'm claiming is the following. The energy of the surface is proportional to the number of particles on the surface. The energy of the system is proportional to the number of particles in the system. So in order to relate how E surface is small or big with respect to a system, I need to relate the number of particles at the surface to the total number of the particles in the system. How I can do this? So I'm saying that the density at the surface multiplied by the surface area is what? Is the number of particles at the surface. Now, surface area it goes like L squared. What is L? It's the length of the system, for example, or the size of the system, linear size of the system. Okay? This goes as L squared. So this is constant. This is proportional to the some specific side to the second power. What I obtain from here that n surface that L is proportional to n surface to the 1/2. I'm sorry. So we have that n surface is just proportional to L squared. Energy is proportional to n surface. N surface is proportional to surface area multiplied by the density. So we have a proportionality between the number of particles on the surface and the size of the surface. Great. All right. Now let's find how L is related not to n surface, but to the total number of the particles. Okay. So we also can say that density in the system multiplied by system volume is proportional to n. System volume is proportional to the L to the third. Right? What we obtain is that n is proportional to L to the third, or n to 1/3 is proportional to L. Now we have two proportionality. N surface is proportional to L squared. L is proportional to n to the third. So what we obtain is that n surface goes like n to 2/3. Okay, so the number of the particles at the surface is proportional to the total number of the particles to the 2/3. We know that E surface divided by E total goes like n surface divided by n, which goes like n to the 2/3 divided by n goes to n to the -1/3. 1/3. So the ratio between the surface area and the surface energy and the total energy is the number of the particles in the system to the -3rd power. How many particles we have in our macroscopic system? Avogadro type of a number, right? So n is of order 10 to the 23, 20 to the 30, 24. The ratio between those guys becomes of the order of 10 to the -7. Okay? So it's the 7th point after the decimal point. The 7th number after the decimal point is what surface area is for macroscopic systems. So if we're comparing energies and we want to say, well, energy is extensive property, well, not exactly, because you have surface area and between two phases. And for those surfaces, you have an additional energy, and you have to take this into account as well. Well, one can say this contributes such a small quantity as 10 to the -7, order of 10 to the -7, that it is completely not important. And for now, if we're comparing surface energy to the bulk energy, we will just neglect it. Okay, so next week, we will continue our path into phase transitions. Thank you.